Great to see you here again. We have another video related to prime numbers, number theory, and divisions. And now we're going to talk about what we call the greatest common divider and least common multiples. Now, these are two elements that we will define here and that we will use later. And we also will use some or identify some relationships between the greatest common divider and the least common multiple. Now, when we are looking at the greatest common divisor is in fact, when we look at two integers, the GCD is the largest integer that divides both integers. Now, we have to find out which are those, and for small numbers it's easy to find, but for larger numbers this becomes more complicated. Anyway, when we are going to factorize the numbers using the prime numbers, it will be easier to find the greatest common divisor even when we are looking at rather large numbers. Now, when we look at the definition of the greatest common divisor, we look at the non-zero integers a and b, the largest integer d that divides both a and b. We can say it as d divides a and d divides b, is the greatest common divisor, and we write it as d is GCD of a and b. So basically that's the definition, but the problem is how to find it. Now what we can do is to look at the positive common dividers of the two integers that we are considering. So we're just looking at, for example, at the numbers 12 and 20, and you can find, or you can say that the divisor for 12 for a are 1, 2, 3, 4, and 6. For 20 we have 1, 2, 4, 5, and 10. And we see that we have common divisors here, which are 1, 2, and 4. And we say that the GCD is in fact of 12 and 20 is equal to 4. So that's the greatest common divisor that we have in those two numbers. Now, when we look at the greatest common divisor and what we also call pairwise relatively prime, when we have the greatest common divisor, and that greatest common divisor is 1. So we can have composed numbers, which are not prime numbers, that do not have any divisors in common. And when they don't have any divisors in common, we can say that the GCD, the greatest common divisor of those two numbers, is equal to 1. Let's consider two numbers, 15, which we can write as 3 times 5, and 121, which we can write as 11 times 11. In this case, because there are no common divisors, the greatest common divisor of those two numbers of 15 and 121 is equal to 1. Now, when two numbers have as greatest common divisor the number 1, then we call them relatively prime because they don't have any of those numbers in common. We cannot divide it by them. They're not prime number, but they're relatively prime. Now, when we have applications and we find, in fact, in a set of, let's say, when we have two integers in a set of integers, we try to find those integers that have a common positive divisor greater than 1. So it's basically important to define the concept of pairwise relatively prime. So when we have the integers a1 up to an, they are pairwise relatively prime if the GCD is equal to 1 of the numbers ai and aj, and that's whenever 1 or I and j are between 1 and n, and j is larger than n. So we take different numbers, we take different integers, and we try to find those integers which have a GCD equal to 1. So basically, that's the concept of pairwise relatively prime. Now let's look at some numbers. We have 15, 74, and 101. Those are the three numbers that we have. And we can say that the GCD of 15 and 74 is 1. They don't have any divisor in common. The GCD of 15 and 101 is also equal to 1. And the GCD of 74 and 101 is also 1. It means that 15, 74, and 101 are pairwise relatively prime. So it's a very important element to understand. We will use it later in some applications. Now we are going to use the greatest common divisor and apply it to prime factorization. Prime factorization is a technique whereby a positive integer is written as a product of prime numbers. When we look at two integers, a and b, we can write them as a is equal to the first prime to the power a1 multiplied with the second prime to the power a2, and so on up till we reach all the primes that are relevant and their relative powers. We can do the same for b, and we can say that some of those parameters, powers in this case, ai or bi, can be zero when the prime number is not part of the factorization. So let's have a look how we do this when we have two numbers. We have the number 2975, which we can write as a prime factorization. I didn't put there the first prime 2, but we could put there 2 to the power 0, which doesn't really have a sense here, but I put here the prime numbers that are common in the two numbers. So the first one I write here is 3 to the power 0, because 2975 cannot be divided by 3, but it can be divided by 25, by 7, and by 17. So I have the factorization 3 to the power 0 times 5 to the power 2 times 7 times 11 to the power 0 times 13 to the power 0 and times 17 to the power 1. I could have left out those primes which have a power equal to 0, but I just leave them here so you see all the primes that I'm considering and that some of those powers are indeed equal to 0. The second number that I have is 6375, which can write as 3 times 5 to the power 3, plus 7 to the power 0, 11 to the power 0, 13 to the power 0, and 17 to the power 1. Now, based on this, what we also have is that we can define the greatest common divisor of two numbers as the product of the primes and the powers, but when I have the different primes, I take the minimum of the powers of the two numbers. So I have P1, I find it in A and in B, and I use the power which is the minimum of the power of P1 for A, A1, or the power of P1 for B, B1. And I do that for all the relevant powers that I have. It will be better if I show you on the example we have above. So when we have the greatest common divisor, we can say that the greatest common divisor between 2975 and 6375 is 3 to the power, the minimum of the powers of 3, which are for A 0 and for B 1, multiplied by 5 to the power, the minimum of 2 and 3. So in 2975 we have 5 to the power 2, and in 6375 we have 5 to the power 3. We have the next one, which is 7. We take the minimum between 0 and 1, and then we take 17, and the minimum there is between 1 and 1. So I took out 11 and 13 because both of them have no power, let's say, are not part of the factoring of any of those numbers. So I have to take 3, the minimum 0 of 1 is 0, so it becomes 3 to the power 0. 5 and to the power minimum of 2 and 3 is then 5 to the power 2. 7, minimum of 0 and 1 is also 7 to the power 0, and for 17 I have the minimum of 1 and 1, so we take 17 to the first power, and when I look at this, we find that the greatest common divisor is basically 425. Now, we can also find, let's say, the least common multiple. And the least common multiple of two positive integers a and b is the smallest positive integer that is divisible by both a and b, and we write it as the least common multiple of a and b. LCM is the abbreviation. So based on the prime factorization, we can say that the LCM is of two numbers a and b is in fact, when we look at their prime factorization, instead of taking the minimum of the coefficients of the common prime numbers, we take the maximum. So when we look at two numbers here, 2975 and 6375, we take the elements from the previous slide. So instead of saying 3 to the power 0, now it's 3 to the power 1, 5 to the power 3, 7 to the power 1, 17 to the power 1, gives us a number of 44,625, which is the least common multiple of the numbers 2,975 and 6,375. Based on this, we can define, or we can prove that there is a relationship between the greatest common divisor and the least common multiple, is in fact that when we say that we multiply those two integers, that it's equal to the greatest common divisor of a and b multiplied with the least common multiple of a and b. So that's a property that we could prove, but let's take it like this, and we can find the proof in some other parts of some publications, but we will not look into it in this series of videos. So that was what I wanted to say about the greatest common divisor and the least common multiple. What we're going to do in the next session is to introduce you to Euclidean algorithm, which is a very important algorithm that we can use to find the greatest common divisor. You're doing a great job, and I'm looking forward to seeing you in the next video. Thank you, and bye-bye.